excited to be here. Feel free to interrupt with questions anytime. So today, maybe ambitiously, maybe with a little lack of humility, I want to explore the question of how can we trust machine learning. And as Anthony mentioned, I joined Stanford about a year ago. And in the process, I had to share all my teaching evaluations for all the classes I taught over the last 15 plus years. And I strategically hid this one. It says, Professor Guestrin, I'm very disappointed in your class. I thought machine learning was going to be magic, but it's just math. And I call this the math myth of machine learning circa 2008 when I got that teaching evaluation. And there, we thought that you could start with some data, you do some machine learning magic or math, and you end up with profit, which at the time meant showing that my curve was better than your curve, and then writing a paper at a top conference about it. Now, this seems all well and good, but there must be some magic in machine learning. I mean, we're making a huge difference in the world, from solving games that have never been solved before, to self-driving cars, and living a healthier day using devices that use machine learning and AI. Now, to me, the magic in machine learning is what happens in the spaces between the math. That is, how you define the problem, how you collect or clean or set up your data, how you define or choose your model, how you integrate that into an overall system, how you deploy that system, and how you evaluate and measure it along the way. There's math in this, but the typical math that we think about is a small component of an overall system. And each step of the system is filled with complex human decisions that are getting harder and harder because this machine learning is becoming more and more of a part of every decision that we make. And the systems are getting more and more complex. It's important to step back and ask the question, how can we even trust machine learning? And one way to think about this is to step back further and review the question of how do we trust? How do humans trust? And I love the seminal work by Tom et al. That looked at medicine and said that if you have trust in your provider, say your doctor, you have increased adherence to the treatment, you continue with the provider longer. But if you don't have trust, you don't seek care. You don't seek preventive care, you don't seek surgical care. And this leads to detriment in the long run. So they define 3 areas of trust. Technical competency. Does my provider, does my doctor know what they're doing? Interpersonal competency. Do you communicate well with me about what they're doing? And the third one is agency. Do they have my best interests in mind? And so, inspired by this and the work that we've been doing in machine learning, I've been asking myself, what are the core principles of trust in machine learning or AI? And here, I'm thinking about trust for whom. So, can I, as a developer, trust the things that I'm building? If you're using what I built for you, can you trust what I built? And then as a society or as a community, can we trust what we're building? Are we doing the right thing for humanity in the long term? These are big questions. And today, I'll focus a little bit on the first question. Can I trust what I'm building? And I'm proposing 3 principles of trust inspired by all the research that's been done in the area more generally of humans. First one is clarity, second one is competence, and the third one is alignment. So clarity, to start, is really the property of being well understood, of communicating well with each other. So to explore this, as a machine learning engineer, things are pretty simple. You give me a function f, I'll optimize it the best I can. I'll stay up all night, I'll forget to eat, but f is going to be as big as possible. But the problem here with trust is, have I picked the right F? Have I figured out the right problem that I'm trying to solve? So let's do a little user study based on a much bigger user study that we did some years ago. And this was when I was part of the University of Washington still. And the mascot for the university is a husky. So every time there's a game, we brought a husky to the stadium. The real problem is that if we by mistake brought a wolf, then thousands of people might die. You might think this is a funny example, but it's real. So we got together with the senior leadership of the university, and we decided the best way to solve this problem is to build a neural network that would predict if it was a husky or a dog or a wolf that came to the stadium. And as a community, we decided 95% accuracy was the best possible, was the right metric for us. In other words, we decided if 1 in 20 games, thousands of people die, that's okay. That's an acceptable risk. And so my question to you is, I have a model, it meets the requirements, the safety requirements that are defined for this problem. Do you trust this model? Raise your hand if you trust the model. Meets the requirement. Clark does not trust the model. Raise your hand if you don't trust the model. If you don't trust the model, is it because you don't trust me? Raise your hand. Raise your hand. You don't trust me. Thank you.
I trust you, I don't trust your machine learning.
You don't trust my machine learning. But why? You meet the requirements. I'm sure you learned in this class that you set up some safety levels. You might have multiple metrics. You meet those metrics, and you're ready to deploy. Yeah?
I'm not sure if this is the right metric. I think like sensitivity versus specificity, I wouldn't summarize it as just accuracy as a metric.
Makes a good point. Says this is not the right metric. But the senior leadership of the university decided that this is the right metric. So one of the questions is this the right metric? And we'll talk a little bit about it in the third section of the talk. But even before then, if you pick the right metric, even if you meet it, it might worry that you're not measuring the right thing. So in this case, what my student Marco Ribeiro did was try to come up with a method to try to understand why a machine learning model makes a particular prediction. And so what you're seeing here in this next slide is the prediction, the image and the prediction made, which was a husky, and the parts of the image that the model thought were important, this approach thought were important to make this prediction. And I'm going to show you examples from predictions of wolf and husky. And what do you notice? Yes?
Well, I've read the lying paper, so I know it's...
You know the answer, so you know.
It's looking for snow.
Cheated. And we'll remember that at the end of the quarter. But he's correct. If you see here, I haven't built a wolf detector. I built a very deep and fancy snow detector. In other words, there was this spurious correlation between wolf and snow. Whenever there was a picture of wolf, most typically it was in snow, that was giving us the high accuracy. And it doesn't snow very often in Seattle, so it's unlikely that when the animal mascot will come in, there will be snow to help us ground the predictions of wolf. So if Socrates via Plato said, unexamined life is not worth living, I say that Marco would say, an unexamined model is not worth using. So part of this, of clarity, is about this property, the quality of being easily understood, the quality of examining why you're making a particular decision and whether you're doing it for the right reasons. And as we thought about this. The first way we've approached this is through clarity v interpretability. So interpretability is about giving humans a mental model of the behavior of machine learning models. So if you might use a simple model like a shallow decision tree, it's very easy to get a mental model of what's happening. But the problem is, this model might not be particularly accurate. So you can make the decision tree bigger. Now it's a little harder to interpret it, a lot of if and then rows, and it's a little more accurate. And there's a trade-off. And there's been some field of study of trying to find more accurate interpretable models. But the problem is that real-world use cases and superhuman AI that focus on accuracy tend to leave us with a complete lack of interpretability. And the question we approach from that original work, which has led to thousands of works in this area, is to ask, can we provide some transparency or interpretation to even the most accurate state-of-the-art models? So our first endeavor said, let's ignore the internal structure of the model, consider a black box, so we can examine any state-of-the-art model. We can compare existing models and future models, and models from different classes. And so in the first paper, which you mentioned, Lime, well, the insight was, if you take a prediction, it might be very complicated in terms of what the decision space looks like. But if you zoom in around the prediction, and if you zoom in some more, the space might look simpler or locally linear. So can we fit a simple model around each prediction that helps us explain what's happening? So if you take this confusing image and you give it to an image classifier, now we can interpret its behavior. Can say it predicts it's an electric guitar with probability 0.32, and then it's looking at this part of the image. It's predicting it's an acoustic guitar when it looks at this part of the image, and a Labrador when it's looking at this part of the image. And thus gives us some sense of what grounding we have for the predictions. Now, if we go back to this user study that we did together, thank you for signing the release form when you came in, by the way. And we made it much more formal, and we worked with 27 subjects. Before seeing explanations, about 60% of subjects didn't trust the model because none of them trusted me. And about 40% had this no insight. After seeing the explanations, 26 out of 27 no longer trusted the model. Sorry, 25 out of 27 no longer trusted the model. And 26 out of 27 had this no insight. So the question I always ask myself is, who is that person who had this no insight and still trusted the model? But as you can see, by providing explanations and an ability to interrogate a model better, you can discover, for example, spurious correlations in the data that are impacting the behavior of the system. So really, the first part here is to try to provide some transparency, to give humans a mental model of the behavior of a system. And Lime was the first endeavor in this space and assumed this locally linear behavior. There's been a lot of follow-on work with a lot of different assumptions and algorithms. One little example I like to give you just to show an alternative here is what we call anchors. This is about finding sufficient conditions for a prediction. In other words, if I were to move the input anywhere in this box, I will still make the same prediction. So let me show you an example of that. For this prediction in image classification, I would predict a beagle if I fix these areas of the image, no matter what happened to the rest. Now take another task, which is the visual question answering task is really cool. You give me this image, and you ask, what's a mustache made of? It says banana. That's really impressive. Or how many bananas are there in the picture? And it says 2, which is also really impressive. But if you look at the anchors, there's sufficient conditions for a prediction. For the first question, it's the word what. And for the second question, is the word many. In other words, any question with the word what gets answered banana. Like, what's the ground made of? Banana. What was the head of the US? Banana, and so on. And any question with the word many gets the answer 2. Like, how many people in the picture? 2. How many is too many? Obviously 2. And so these notions of anchors, interpretability, help us understand brittleness in the system that you normally would not detect with standard test procedures. So clarity can help machine learning help humans make more informed decisions too. So here's a great example that I was not involved in, where they were using similar kinds of explanations in the operating room to detect when the oxygen levels go too low, so hypoxemia. And not just providing a prediction, but providing predictions plus explanations helped doctors be more effective in their efforts. So that's clarity. The second area of trust is competence. A competence is about having sufficient skill or knowledge for a particular duty or in a particular respect. So sufficient skill for a particular duty in machine learning is about evaluation. Does this model have the skills we're hoping for? Now, in 2008, this was very simple. I showed that my curve was better than your curve on a benchmark data set, and that was sufficient skill to get my paper published. But even this notion of a test set is naive in practice. In practice, data is changing all the time. You have sometimes little insight of how the system might behave in the real world based on the training that you do offline. So benchmark data sets and test data sets are at best a weak proxy of what's going to happen in the real world. And so to me, we need to rethink how we evaluate these models in practical settings and learn from software engineering, where we do things like failure analysis and more systematic testing of software. So what does that mean? Let me just give you a couple examples. In terms of failure analysis, one of the tasks that we looked at is, can you perturb the input adversarially in a way that will change the prediction? So there's been some work in this area. For example, you give me this image and the model predicts a panda. You can add some imperceptible noise, and now it predicts a gibbon with high confidence. Now, this is really interesting work, but this is more for like an adversarial attack setting, maybe for security. But it's not the kind of noise that you typically see in the real world. Our question was, what kinds of noises or perturbations are natural that really will break the model? So let me give you a couple examples of that. So again, visual question answering. I give you this image and say, what type of roadside is shown? And it says a stop sign. Or I give you this paragraph and ask, how long is the Rhine? And it says 1,230 kilometers long. Now here are some small perturbations. So for the first question, I changed it from what type of roadside is shown to which type of roadside is shown. And now it's do not enter. And I changed the second question from how long is the Rhine to how long is the Rhine? By adding an extra question mark, and it's now 1,050,000 long. And so this is the kind of natural variability you see in language that is really breaking the model. So we asked ourselves, and this is also Marco's work, how can we find semantically equivalent adversarial examples? And the way we approach this is by using paraphrasing models to perturb the input but retain the semantics, and then figure out which ones would break the behavior of the model. So let me show you an example of that. Again, visual question answering. Give me this image. I ask, what color is the tray? And the model says pink, which is pretty impressive. But I start paraphrasing it. For example, I ask, what color is the tray with a British accent? And it's now green. Or which color is the tray? And it's now green. So these are natural variabilities that are semantically very similar, but they lead to changes in prediction. And this is a problem, typically a problem in terms of coverage of your data. And so detecting it lets you do nice things. So for example, you could do data augmentation. And if you do that in very simple ways, you can significantly increase the robustness of the model once you discover these issues. So machine learning models are prone to bugs, and we really need to find semantically meaningful ways to discover these issues, test for them, and improve the behavior of models. But really, how do we know when we're ready to deploy? This is a big question in general. And I think we need to test models more systematically like we test software. So inspired by software testing approaches, we came up with this methodology we call checklist, which is pretty simple. So let me give you an example. So let's say you have an input sentence like, easily the best airline in Seattle. Actually, I should change it to, easily the best airline in San Francisco. And I give it to a sentiment classifier, and it says it's a positive, neutral, or negative sentence. Very simple task. How do we test that? If we're software engineers, we start from testing small units of behavior. So for example, in NLP, you might have different vocabulary, named entities, negations, and so on. So what checklist does is a methodology for creating tests along different categories like this. And based on the skill set that you want the model to have, you can get some checks and crosses and decide when you're ready to deploy. Now let me show you a couple examples of tests and what happens. The first one is minimum functionality test. This is kind of no-brainer. You expect everything to work just fine. So for example, in sentiment analysis, I give you a positive sentence, it should be positive. Or a negative sentence like, I despise that aircraft, it should be negative. Another one is negation. So I gave you a negated neutral sentence, and it should be neutral. So this is not an international flight. Now, if you generate simple tests like this, and you give it to public APIs or state-of-the-art models, they fail at rates of up to 15%, even though they're very simple tests. Or with negation, they can fail at rates up to 54%. The second kinds of tests you can imagine are metamorphic or perturbation-like based tests. So for example, you have an input that has a location, like I'm taking a flight to Chicago, and now you change your flight to Dallas. Maybe you have feelings about Dallas versus Chicago, but in general, the sentiment should stay the same. Nonetheless, state-of-the-art models and public APIs fail at rates of up to 20% when you do perturbations like this. Or finally, you can imagine changing sentences, changing the direction. So for example, if you have a positive sentence, you add another positive sentence, it shouldn't get more negative. But despite that, simple perturbations like this cause models to fail rates of up to 34%. And these are models that people are paying money for in public clouds. So what it says to me is we haven't had a systematic way to evaluate these models before we ship them. And what Checklist does is a methodology and a tool to make it easy to detect and build tests like this. And we did a user study with engineers that work on a real problem like this. And using the methodology and the tool, they were able to generate more tests, more test cases per test, and detect more mission-critical bugs on the system is already deployed in a short period of time. So competence is this really property of having sufficient skill for the task at hand. And is the second anchor pillar of the three principles of trust here. The third one, which is the most complex one, is alignment. So alignment is really about having a state of agreement of cooperation between peoples or parties for a common cause or viewpoint. And the key here is a common cause or viewpoint. Does my AI, does my system have the same cause or viewpoint that I hope to have? So again, 2008, very simple. We had totally aligned principles. We want to get a paper into the conference. But these issues can get much more significant when you start building real-world systems. And Netflix articulated this really well. So they're recommending content for you all the time. And they had this challenge in 2006, which was really popular and really put a lot of effort into recommender systems. And the idea here is you're given a data set of movies, and you had to create a model to predict what rating a user would give to a particular movie. This was extremely useful for them in a sense that there was a lot of work in recommender systems, yet they didn't deploy this in their actual systems. And the reason is, this is not the metric they care about in their business. The metric they really care about is churn. What is the chance that next year you'll cancel your Netflix subscription? And predicting your rating doesn't help me too much with respect to churn. Based on a variety of methodologies, they discovered a metric that did make sense, and it's binge watching. So if you click on something and you binge watch it, you're a lot less likely to churn next year. And so they decided to create a metric which is to maximize the probability that you'll click on something and watch it to the end. And optimizing that was closer to the business metric they cared about. Now, I call this the loss metric gap. The loss function is what we optimize in machine learning. The metric is what we actually care about for the things we build. Now, you could switch a loss function, like increase the probability of binge watching and get closer to the metric that you care about, churn. Or you could try to find some other smooth approximations of the metric you care about and try to get closer to the loss function. But the problem is that there are typically multiple metrics that you care about. They're complex, and fundamentally, as a machine learning engineer, you typically don't own those metrics. It's often a product team that's deciding how to evaluate the overall system, and you don't see all of that, or you don't necessarily have access to all of it. So it's a really complex process. So what we did when I was still at Apple is come up with a simple methodology to solve this problem, to address this problem. And the idea here was, can we come up with a parametric family of loss functions that you can evaluate against the metric that you really care about? During the training process, as you're optimizing the model parameters, every so often you go back and you reevaluate the metric you actually care about, like churn. And then you use that to update the model parameters and get them the loss parameters and get them a little closer to the metric you care about. This simple procedure was very effective, but this issue of loss metric gap is getting more and more complex. So for example, if you think about foundation models or large language models, or the idea that we're training these really complex models and reusing them in many ways, now we have an even bigger gap because we have a model that's been trained, for example, with a language model loss, which has some gap to the prompting loss that you use, which has some gap to the metric that you use. So the bigger, the more complex the system becomes, the harder it is to align it with the behaviors they care about. And doing this is hard, but important. And in fact, there isn't a single metric we care about. Like we saw in checklist, there might be multiple metrics we care about, and we have to somehow figure out how to trade off between all of them. And that's even more complicated. And alignment is about agreeing on how to balance the different concerns. And we got an example earlier, we talked about sensitivity versus specificity. That's a different set of concerns. And they can sometimes go against each other. So let me show you a very simple example of that. So one of my teams at Apple came up with this feature for the watch where instead of having to say an activation word for the personal assistant, you could just use a gesture. So you could say, what's the weather today? On it. I don't know if I have internet connection, but it did detect it, and it's thinking. And just based on the gesture, it was able to evoke the personal assistant. And this is really interesting. And you have to think about what metrics you care about. So for example, a false reject is a missed gesture. So I raised my arm, and it did not detect me. That's kind of a little bit of a problem. But a false accept is a big problem. This is when I'm giving a talk, I'm gesticulating a lot, I'm being Latino, and then suddenly Siri speaks up. It's like, I didn't hear what you said. It's like, you're so stupid. And the problem is, I spend much more time gesticulating and talking than I do evoking a personal assistant. And so false accepts are a much bigger concern. So when you're thinking about a product, you have to think about the trade-offs between the different criteria that might arise. The way that we did that was we trained a bunch of models, and we came up with a set of product decisions. So we're going to have less than one false accept per week. So that's one time per week. My weird gestures evoke the personal assistant. Try to make the false rejects as small as possible. But even that simple trade-off was really complex. And in reality, what we're trying to align is not that just simple trade-off, it's all sorts of values that you might care about, like the accuracy of the system, like false positives, false negatives, sensitivity, specificity, but more. As we've seen, machine learning can have a disproportionate impact on different populations around the world. This has been discussed, for example, a lot in recidivisms, this recidivism setting, where black defendants were much more likely to have predicted to be committing a crime again than white defendants. So there might be many criteria you care. Like in fairness, there are multiple criteria, and there was for a while a formula for writing papers. We say, here's 3 criteria, they all make sense. And here's an impossibility theorem that says you can't satisfy them all at the same time. Now, what that means is not that it's something you give up on, but it is that you have to make complex trade-offs that express the value system that you care about. And today, there's no really good way to think about machine learning as a multi-criteria optimization problem and how these trade-offs can be made. And every choice that you make as a developer, every choice that you make when you create systems impact the world, impact people, and they have to be aligned with what you're hoping for. So, for example, I often ask myself, what am I teaching my models? Maybe I should ask, what am I teaching my kids? So here's some time ago, my kids were watching a show that they loved and I hate called Paw Patrol. In this show, there's 6 puppies, they go on life-saving missions. There's only one girl puppy, Sky, who is dressed in pink and almost always in the sideline watching while the other puppies save the day. This is not the kind of model that I want to share with my son or daughter. And as we're experiencing more and more of the world through devices, it's important to think about how our values are aligned. And again, the data and the choice of data is one of those important decisions that defines the behavioral machine learning model. And this is not a new problem. So before digital photography, we used to use film. So there was this plastic canisters with a little thing inside. You might have seen this, no? And you had to send it to a lab to develop and get your prints. And the labs around the world, and Kodak, that was the biggest producer at the time, had to make sure that the chemicals in those labs, they had different temperatures and humidity and so on, were calibrated to give good pictures. The way they did that is they created these cards in the 40s and 50s, which they called Shirley cards. You can see a bit of sexism there already, too. And they were always a light-skinned female model that was used to calibrate the pictures. And so what that meant is for people with lighter skins, the photos look great. But if you had darker skins, the photos were overexposed. And you can really see that when you have photographs with folks with lighter skin tones and darker skin tones in the same image. And it wasn't until the 80s and 90s that they started using cards with folks with different skin tones in order to calibrate chemicals. So this is an example of how diversity of representation in data is really important. But it's not just about the data that we collect and we use to train a model. Every choice that we make in the development of a machine learning system has to be aligned with the values that we're hoping to exhibit in the world. Let me show you a final example here. Machine translation. It's amazing. With neural machine translation, you can translate between a large number of languages. But you can also be faced with very significant issues. So for example, if you go from a non-gendered language like English to a gendered language like Latin language, for example, Portuguese, you can get this kind of behavior. The doctor called the nurse gets translated to the male doctor called the female nurse, which will perpetuate a number of stereotypes. Now, the issue here is, in Brazil today, about 57% of the doctors identify as male. Now, the ratio of doctors that identify as female is increasing rapidly. But today, if you do a hard translation like this, anytime that more than 50% of the doctors are male, then you're going to get a male translation, the male form. And so, even if we had infinite data, if we design a system this way, we'll always be perpetuating the stereotype. So, even in this setting, we have to think about alignment as how we're going to represent our values in every decision that we make along the way. So stepping back, I think we need to think carefully about what are the principles of machine learning that can help us address trust and making trustworthy systems. And I'm glad you're here this quarter discussing this. And my proposed framework is around clarity, competence, and alignment. And with that, thank you, Anthony. Thanks for having me. And I'm happy to take some questions and discussions. Yes?
Thank you for your talk. I like your animations.
I'm glad to serve.
Yeah. Could you talk about the interaction between these three different categories? Like, for example, to what degree do you think clarity helps with alignment?
That's a really great point. You'd think that you'd want to create orthogonal axes, but the axes are not necessarily orthogonal. So, for example, I think they build on each other. So, to understand alignment, part of it is that you want to evaluate competence along multiple metrics that you care about. And part of evaluating competence or understanding where the model is working, is not working, and building trust, is the notions of clarity. So to me, these are more like layers that build on each other. So for example, you asked about the relationship between clarity and alignment. I would like to be able to understand who is being impacted by something. Or if you're making trade-offs, who is benefiting and who is not when something happens. And you can think about this from a fairness perspective in terms of group fairness. So what groups or populations, let's say blacks, Hispanics, for example, or typical ones that are discussed in terms of race, are impacted by the decision models in a disproportionate way compared to whites. But you also might want to ask about individuals. So how is the treatment that you're getting relate to the ones that everybody else is getting in this class? Is Anthony being fair to you? And can we make that more clear or transparent? And so part of that is about what values we want to reflect in the system. Thank you for that question. Others? Yes.
So you and your team did some of the seminal work on explainability methods, and I forget what year exactly that was, but like, where have things gone since then, and what are you most excited about in terms of emerging algorithms and whatnot for explainability?
Yeah, it's I can tell you what I'm excited about, and I can tell you what I'm concerned about. So what I'm excited about is that there's been a tremendous amount of focus on this, and a number of different methods or ways to think about explanations. So for example, in Lime, explanations are about what features in the input, this is called feature importance, or feature attribution. So what parts of the input are important. There's others have asked, can we use examples or data points to help explain a prediction? Some folks ask, can we use what are called concepts? So these are not neither features nor data points. These are things like, when I predict zebras, am I using the fact that zebras have stripes in order to make the prediction? So there's been a lot of exploration in terms of what kinds of modalities are important for explanations. There's been great exploration in terms of making these algorithms more robust and faster and more scalable. Some are model agnostic, like what I talked about, where you consider the model a black box. Some of them have been opening up the box of the model and using the insight to help make these things better or faster. So all that is great work, and I'm very excited about it. I think that the biggest concern I have, and I think we made a mistake 6 years ago that's been reproduced often, which is a lot of these methods go from the explanations forward. So they say, oh, isn't it cool we can explain this way? Isn't it cool I can have this other notion explanation? Isn't it cool that I can make it faster? But almost none of them start from the decision backwards. So what decision is a human making? Like, is the human deciding whether to intervene on a patient or not? Is the human deciding whether or not to join Netflix? What is the decisions being made? And how do explanations support that decision? So one of the things I'm most interested now is to think about the decision-making process. So how do humans make decisions, and how can they make more informed, data-driven decisions based on things like explanations? And I think that that's kind of the biggest open question today, in my opinion. Yes.
I guess this might be a little beyond your talk, but in alignment you mentioned that you have to kind of figure out trade-offs between values. And I was wondering, when such a resolution is not possible, how do you reconcile things? So for example, you gave the machine translation example, right? Would the fair way of translating it be a female doctor and a male nurse? Or male doctor, female nurse? Like, I guess in my view there isn't really a resolution either way. And what happens when your values might be in direct contrast? So for example, if Netflix wants to make sure that users binge watch their content, but users' interests are perhaps different, is there any way to kind of think about resolving these things? And I think it also comes up quite a bit these days in the tech world in the case of privacy, where companies' interests would be different from the users' interests. So yeah, is there any way to kind of think about that?
really appreciate your question. So thanks for bringing it up. And I teach a class on the ethics of AI, and I see a couple of the students here today, so they're getting a double header of me on these topics. But one of the things that we talk a lot in the class is that there's no right answer. There's a lot of nuances. And one of the problems is, as engineers, we're not trained to deal with the nuances. Like every homework that you have has one right answer. There's a rubric. This day is an automated system to evaluate your homework, and you're done. And then when you leave here, when you leave Stanford and you get an amazing job at whatever job you want to take, you're going to have to deal with the nuances of the real world. And as an educator, I feel like I failed, or we failed, to help build up that muscle of trying to lay out the trade-offs and the nuances in these algorithms. And so the first thing, the first step, you can think about this as a mindfulness exercise. The first step is to do what you're talking about. Can we articulate the different perspectives? What are the different values? Who are the stakeholders? What are the different interests that are being represented? Can we understand what metrics different people care about? And so on. And part of what we need to do is that exercise more thoroughly, as opposed to saying, I'm going to pick lambda 1 plus lambda 2 plus lambda 3 and be done. And so can we do that more thoroughly? And that's what an ethicist would do. For example, one of the folks who gave a lecture in the ethics of AI class, an ethicist, Rob Risch, who was a very well-known Stanford professor. And he jokes a lot that people come to him and say, oh, you're the ethicist. Come solve this ethical problem for me. Like, how do I deal with this machine translation? Give me the answer. And he doesn't have the answer. Like, what he's very good at is, what ethicists turned out to be very good at, is articulating the perspectives. Like helping you write down, okay, this is one perspective, and this is what they care about. This is another perspective, what they care about. So there's that process. But ultimately, as an engineer, you're going to make one choice. Like you're shipping a machine translation system, and you're going to pick an operating point or a decision on how that's going to go. And so what I'm interested in is, can we help articulate the process of trade-offs? Can we understand, if you make a choice, since you have to make one choice, who is impacted? So who is going to benefit, who's not going to benefit? Can we articulate that? Can we make that transparent or more explainable in a way that you can understand that? And that happens all over. You mentioned privacy is a great example of that. And I've been involved in very complex privacy decisions that, again, there are no right answers, and you have to figure out what choices to make. So sorry, I have not answered your question, just to say that there's lots of nuances, and we have to be better at dealing with those. Any other questions? Yes. In the section about alignment, it seems like you talked about like aligning loss and metrics, that gap, and kind of these other like current differences in how we deploy our models, how like we intend them to. Do you think, like, I guess, what are your hopes for your research? Thinking like larger AGI, general intelligence stuff. Do you think things like adaptive loss alignment or other algorithms like that also translate to aligning superhuman AI to human values broadly? Wow, that's a big question. So AGI. Before we go to AGI, I'm a big believer in augmentation over replacement. So in other words, how can AI help us be superhumans, let's say, or do things that we didn't think we'd be able to do before. And if you take that perspective of things, so AI as a tool for augmentation, that can get better and better, alignment is incredibly important, right? So I think that's something that, adaptive loss alignment, I think, is a tiny step in this very big problem, because in our heads, we have a set of values we care about. We don't even know how to write them down. And so how do we help translate what's in our head to a behavior of a system? An example I use in the ethics of AI class is a self-driving car. You're probably familiar with the question of, the trolley problem. Like, do I veer myself off a cliff with the car, or do I hit somebody in the road? But take a much simpler question. Do I drive on a windy road fast to get there faster, or do I take more risks? Or do I take a more conservative, kind of safer, but slower pace? That's a hard decision. Does self-driving car.co make that decision for you? Like you step into the car and say it decides to, drive slowly or drive fast or something? Does it ask you to enter your preferences in this, interface with lots of sliders? Can you understand that? Is there something in between? Like, what does that look like? And I want to say that our even for that very simple example, our values are not aligned. And it depends, it's contextual. If I have all my kids in my car, I might want to behave differently than, if by myself. My kids are going to college, maybe I'll behave different than if my kids are young and depend on me. I don't know. And so how do you make this complex contextual decisions in collaborative AI human settings? It's a really hard question. And so I'm very interested in that. And then when you get to AGI, I don't know what you mean by AGI. Do you mean AGI is a human, an entity that is itself sentient and has its own separate value system? Or is it a reflection of our value system? And that's a very complex philosophical question, too. I hope that helps.
All right, let's thank Carlos.
Thank you.